This video discusses Thevenin's and also Norton's theorems. We'll start with Thevenin's theorem because Norton's theorem is really just a source conversion to Thevenin's. So with Thevenin's, the theory is that we can replace any two-point network with a single voltage source in series with a single resistor. And for this to be true, that this single voltage source and resistor have to provide the same open circuit voltage and the same short circuit current to the rest of the circuit. So what you have to understand for Thevenin's theorem and also Norton's theorems here is that the idea is that when we have a complex circuit, we want to try to simplify part of that circuit so that we can concentrate on the rest of the circuit. So if you think about the circuit for pretty much any type of device, there's the section that is designed to basically generate your power and to provide the power to what's a lot of times is just referred to as the load section. So we have this power section here, and this all the components within this power section are usually just there to generate the power at the voltage and the currents required for this load section to perform the actual tasks that we want the load section to perform. And so with Thevenin's theorem, the idea is what we can do is we could take what might end up being kind of a complex sort of power section here and break it down to simply a single voltage source, which we like to call Thevenin, in series with a single resistor called Thevenin. And so we just have this nice simple circuit here with 2 points, call it A and B, and we want the open circuit voltage to be the same and the short circuit current to be the same. And if that's true, actually it's going to be the same for any circuit here. So you see here, like if we break the circuit at 2 points, which I'm calling A and B, then we can just forget about the load section for right now and work on simplifying the power section down to this Thevenin voltage in series with the Thevenin resistance. And then once we do that, then we'll be able to just remove the power section and connect up the Thevenin equivalent, and then we can work on designing or whatever that we need to do at the load section, and we can not worry about all the complexity within the power section. So that's the idea of this Thevenin's theorem, is the fact that we're going to take a complex circuit, we're going to break it into essentially a power or supply sort of section where everything happening on the left hand side is just to provide the proper voltage and current at the points A and B so that we can power our load section, and then we can concentrate on designing, or possibly maybe we already have it designed, but we want to try to optimize or study the load section and not get bogged down by the complexities in the power supply section. Alright, so to do that, we basically just have two things to do. First, we have to find the resistance, the Thevenin resistance, and then the voltage. And I said first, but it really doesn't matter which one you find, which order you find them, but you have to find Thevenin, which is the open circuit voltage at your points A, B, right here. So here's our point AB. And then we have to find the resistance. If I was to put an ohm meter here, to measure the resistance at points A and B, I need to know what that resistance is. Okay, so you're putting either a voltmeter at the open circuit. So you're putting a voltmeter here at your 2 points A and B, or you're going to put a ohm meter and measure the resistance. Now when you do that, let's actually do open circuit first here. So what we need to do is we need to find the open circuit voltage. And I mean, if you actually had this circuit built, you could break it at points A and B. Now notice it has to be open circuit, so you would have to disconnect it here at points A and B, and then you could actually hook up a voltmeter and measure Thevenin, and in the lab we'll actually be doing that. Alright, so for us though here, we have to keep in mind if this here is point A and point B and it's open circuit, then there is no current flow. Right? So current is equal to 0 because it is an open circuit at points A, B. If that's true, then that means there's no current through the resistor R3, so the voltage drop across resistor R3 is equal to 0. And therefore, what we are doing is we need to find out what the voltage here is at this point. Okay, and so this now is, for this circuit here, turns out to be just a simple voltage divider. So we can find out that, you know, we have a 10 volt supply with 2 ohm resistor in series with a 6 ohm resistor, and we want to find the voltage across the 6 ohm resistor. So using voltage divider, we'll find that V2, that's this point right here, the voltage across this resistor. So V2 is equal to E times R2 divided by R total, which is R1 plus R2 for this circuit. And so that's, of course, 10 volts times 6 ohms divided by 8 ohms. And so if we pop over to our calculator to calculate that, 60 divided by 8, we get 7.5 volts. Okay. So Thevenin is the open circuit voltage, which is 7.50 volts. Alright, so we go back up to our Thevenin circuit then, and we can just state, okay, now we know that's Thevenin. That is 7.50 volts. That's our Thevenin for this circuit. So the open circuit voltage at points A and B is open circuit without this load section attached is simply 7.5 volts. Now we can find the Thevenin resistance. And again, it doesn't matter which one you do first because they're done completely separately. So the rule is when you're trying to find R Thevenin, when you're trying to find this resistance R Thevenin, what you need to do is short all the voltage sources. So you take all your voltage sources and you replace those with simply a short circuit. And if you had a current source in there, so if you had a current source in here also, then what you have to do with your current source is simply open circuit. Just remove it. And then put your ohm meter on here at points A and B and simply measure the resistance. Well, when we do that, right, we have that R1 is in parallel with R2. So we get our parallel combination here, R12 is equal to 1 over 2 ohms plus 1 over 6 ohms. And so if we calculate that, R12 is equal to 1 divided by 1 over 2 plus 1 divided by 6, which gives us 1.5 ohms. So this is 1.50 ohms. And then we're still, remember, we're actually looking at points A, B, which is right here. So we have the 4 ohm and then the 1.5 ohms is the resistance. And so the total resistance is the 4 plus the 1.5, which gives us our Thevenin resistance to be 5.5 ohms. Alright, so if we come up here to the top, then we have our R Thevenin is 5.5, and for blackboard we need 3 significant digits, 5.5 ohms. And that is the Thevenin equivalent. So remember, what the Thevenin equivalent says is we can take this nice simple circuit with one voltage source and one resistance and replace this entire yellowed section here with just that resistor in series with the voltage source. Now, Norton's theorem says the exact same thing, except for Norton is talking about source conversions. So Norton is saying that you could have a current source in parallel with a resistor, and so you would have, this would still be your point A and B, just like with Thevenin, but we have a resistance R Norton and a current I Norton. Now, Norton's theorem is simply a source conversion. We've already talked about source conversions, and we know that basically we can go between a voltage source with a series resistor and a current source with a parallel resistance by just taking the voltage or the resistance. The resistance actually doesn't change. So it turns out that Norton's resistance is equivalent to Thevenin's resistance, which in this example would be 5.50 ohms. And then the current, we basically use Ohm's law. So we take I Norton is equal to V Thevenin divided by R Thevenin, which of course is also R Norton. And so we just calculate that. So that was 7, V Thevenin was 7.50 volts, and R Thevenin is 5.50 ohms. And so therefore we can get I Norton, the current, is going to be our 7.5 divided by 5.5 is 1.3636 amperes. And so remember, for blackboard we need 3 significant digits, so it would be 1.36. We would not round up because the number to the right of the 6 is simply a 3, so it would be 1.36 amperes. And so there we have Norton and Thevenin.